Hello, everybody. My name is Torsten Hoefler. I'm from ETH Zurich, and I'm here in virtual Frankfurt today to give you an update about the Machine Learning Day at ISC 2020. And I'm summarizing what happened in the last years, and then I will give a bit of an overview of the speakers that we would have had and that we hopefully can see in the coming year, so hopefully already next year. So let me get to the slides. So what has happened in 2019 and 2020 in machine learning? So let me start a little bit about interesting industry developments. And here we have the long-term player, Google Cloud, that has been going on for a while, as you know. But now the news is that you can actually rent a TPU pod with about 100 petaflops brain float performance, which is quite amazing. Even though it is a reduced precision format, so only 8 exponent bits and 7 mantissa bits, so maybe not suitable for scientific computing, but perfectly suitable for machine learning. So the actual news, and this was nearly a year ago, the actual news is that you can now also buy a mini TPU in Raspberry Pi format, so to say, which unfortunately only supports fixed point, but it supports 4 teraops per second at only 2 watts, quite amazing. So then on the next front is another very big company, Microsoft, pledged $1 billion for OpenAI to support the holy grail of artificial general intelligence. So basically developing models that go way beyond what we are used to today, where we have to fine-tune tasks. I will talk about this in a couple of minutes. So they just recently announced that they built an AI supercomputer, which is quite a respectable machine. So they assessed that it would be in the top 5 of the top 500 list. So it has about 285,000 CPU cores, 10,000 GPUs, and 400 gigabit per second network connectivity. So more you can read in the Microsoft blog. Kevin Scott, the CTO of Microsoft, has given a wonderful talk about that machine as well. So what is going on now in the hardware development side? This is actually something that just recently, again, a couple of weeks ago, was announced, the A100 by NVIDIA. This is a true engineering marvel, I would say. So getting to the nearly maximum size of the reticle that you can build today, so 820 something square millimeters out of the maximum 850, 54 billion transistors, and a very impressive data sheet, as we can see here. So number of SMs is going up. The number of tensor cores is slightly going down as the frequency is. However, the overall performance is just incredibly impressive. So it's also one interesting news item that if you thought as a scientific computing person you could get away without using tensor cores, unfortunately, if you want to achieve peak performance on that architecture with FP64 even, you have to use tensor cores. Then they also have quite impressive memory bandwidths, as you can see here. I don't want to go through all of this. One interesting feat with these tensor cores is now that there's a new format, TF32, even though I would have called it, for fairness, TF19, because actually it only has 19 significant bits that are used for the computation, but it's backwards compatible to 32-bit calculations, which makes it quite interesting for legacy codes. I'm not so sure if this is very useful for newly tuned codes, because at the end what's going to happen with this format is you're going to use the full memory bandwidth of an FP32 or of 32 bits for every single calculation, and you're only performing that calculation in 16-bit accuracy, of course, with a 32-bit accumulator as usual. So that's a wonderful backwards compatibility feature, but I would recommend tuning for brain float probably, but this is something to be discovered in the future. So now we had a very interesting time just in the recent weeks where new application results were showing up, something quite massive. I mean, OpenAI's GPT-3 model, so OpenAI has this history of these GPT models where they train very large transformers in a generative setting, transformer natural language processing models in a generative setting, starting at GPT, then GPT-2 and GPT-3. And GPT-3 is the largest one of those, probably the largest machine learning model ever trained. So it has 175 billion parameters. So if you store this with 2 bytes per value, so just 16 bits per parameter, that's going to be 350 gigabyte model size. Right? That's just a model size. Imagine you want to run inference on this. So even inference is quite expensive, but training is even more expensive. So here VentureBeat assessed $12 million to train that model in just in GPU credits. So there's a wonderful paper that came out of OpenAI on 1st of June in 2020, so a couple of weeks ago, that explains what you can do with this model, and it's quite astonishing. So this model is actually a so-called few-shot learner. And the idea is you have a large trained model that is trained on a very large corpus that was basically grabbed off the internet. And then you don't fine-tune it to specific tasks, but you tune it or you specify the task during inference time. So there's a so-called few-shot setting and a zero-shot setting. So a zero-shot setting is the easiest to explain. It basically behaves like a human. I tell the model, or I ask the model, please translate cat from English to French, and it'll answer you that respective French word. That is a very interesting feature of this network, but it can actually do it, and it achieves state-of-the-art and better results than this for these zero-shot training settings. A few shots basically means that I present a couple of examples to the model. So I give a series of translations, so cat, and then the French term, dog, and the French term, and then I'm asking what pig and the French term would mean, usually in the order of 10 to 50. And then this model also outperforms pretty much all of the state of the art. But we're here at an HPC conference, so you can read this paper if you want to learn about all these wonderful results that OpenAI has achieved with this. They have not done fine-tuning, by the way, because probably it is too expensive. I mean, I would be very, very curious to see what would happen if you fine-tune that massive model. But it's so expensive that they couldn't even retrain it after they found a bug in their data cleaning procedure. So they had to work around the bug, and there are some interesting notes in the paper. But from an HPC perspective, this table from that paper is one of the most important tables. So you can see here the number of parameters is quite massive and has been growing over time. And you can also see the total flops required to train. So we are essentially at 314 zetaflops, and I've made a little analysis what this means. So 314 zetaflop, of course, mixed precision, FP16 and FP32 most likely. But that is 155 years on a V100 if we assume very high performance, like the record performance that has been published. Or that is 400 megawatt hours of that same GPU, or for that single training run, nearly $4 million, assuming zero communication overhead and perfect use of these GPUs. So this is quite crazy. So let me now get a little bit more towards the ML Day, what we had planned for this year. So we had multiple sessions planned. The first one was on machine learning for climate and weather, to be hosted by Peter Dubin, who fortunately sent me some slides that I could summarize what is going on there. But the idea here is that we have the Earth, of course, that we are simulating. And the Earth is really large, as we know. And the resolution is very, very limited because we cannot represent every single air particle essentially in a computer. So we have to have a very limited resolution, typically at the kilometer scale. But unfortunately, the system itself that we are simulating has very chaotic dynamics. So it has all kinds of so-called subgrid effects that are very, very hard to capture in scientific simulations and in the good old way we are doing things. So these processes are simply not resolved. And that is one of the bigger problems. And especially in Earth system component models that are really connected in non-trivial ways. However, what we have there is a very large number of observations. So we have satellite data, we have plane data. Well, okay, we had plane data when the planes were still flying, but I think this is coming back. We have a lot of data that we could train machine learning models on. And the idea now is, why don't we use these machine learning models for multiple different opportunities? And here are some of the opportunities that we could talk about. So we could refine the observation. This is something what the community is already doing. We could refine the data assimilation process. We could help with the numerical weather forecasting itself. So we could accelerate it using machine learning accelerators, for example, the TPU or these low precision tensor cores. And we can then, of course, implement post-processing and help with post-processing and make simulations even less required, or improve the data that comes out of the simulation. So this is actually something that we have done in my lab, if you followed the recent work, in collaboration with Peter Dubin. So then the second session was to be organized by Ryo Yokota from Tokyo Tech, and he invited a set of wonderful speakers. So first, Boris Ginsburg from NVIDIA, talking about the latest, greatest developments in stochastic layer-wise gradient descent methods, and how to, of course, accelerate this with NVIDIA GPUs. One of his PhD students looking at second-order optimization or higher-order optimization in general, which can not only lead to more accurate models, but it can also lead in certain circumstances to a higher performance. This is a very, very interesting research direction that we are also embarking in. And then Yang Yu, who just graduated from Berkeley and is now taking an assistant professor position on how to work with very, very large scale systems. So using the LAMP optimizer that we all know and love. So the third session was organized by Mariam Denavi and Tal Ben-Noon. And here they invited Amir Golami from Cord Kreuz's group to talk about their integrated approach to deep neural network design. So they have a very nice set of methods where you can that you can combine into a tool chain to do end-to-end training, so to say. And then Zhang from ETH Zurich, who was going to talk about various ways to implement distributed training, ranging from centralized synchronous to synchronized asynchronous, and then to various decentralized synchronous and asynchronous training methods. So we hope that we can have all these speakers appear in the forthcoming years, and we can listen to what they have to say. So that's all from me with the short summary of what would have happened, what happened last year, and what would have happened in the ISC Machine Learning Day. So I'm really hoping to see you next year, that the situation clarifies. And with that, thank you very much for listening, and yeah, hopefully see you around. Bye.